Alright, thanks for watching, and today I would like to do a very fun exercise about this linear transformation extension theorem. So, let's show the following. Suppose, again, everything is finite dimensional, so V and W are finite dimensional vector spaces, and moreover, V is much bigger than W, at least in dimensions. So dimension of V is greater or equal to the dimension of W. And moreover, suppose you have a subspace of W. So maybe let me start writing down some of the assumptions. So we have V. So we have V that's much bigger than W. So maybe let's make it slightly bigger. Okay. So V is bigger than W, and let Z be a subspace of W. Okay. And it's possible it's all of W. Okay, so let Z be a subspace of W. Then here's the cool thing I want to show. I want to show that there is a linear transformation from V to W that takes all of V and maps it to Z, sorry. So it takes all of V and its image is precisely Z. So show, by the way, there are many of those. So for example, so show there is T, V and W. T from V to W linear such that the range of T equals Z. So in other words, T takes all of V and maps it to Z. And by the way, this would be wrong if V is smaller than W, because suppose V is R2 and W, which is Z, which is R3, then it's impossible to find a linear transformation which takes R2 and puts it into all of R3. So that's a problem, and I think you just need that actually not dimension V is bigger than the dimension of W. You basically need V is bigger than the dimension of Z, but it's not what we worry about. And how do we do this? So has to do with this linear transformation extension theorem. And what is that theorem saying? It says if you know T on each basis vectors, then you know exactly what T is. So let's say V1 up to Vn be a basis of V and let's say Z1 up to Zk be a basis of Z. And what do we know again? Dim V is bigger than dim W, so in particular dim V is bigger than dim Z because Z is smaller than W. So we know for sure that N is greater or equal to K. And what we would like to do is define a linear transformation as follows. Define T from V to W as follows. Okay, maybe let me draw a little picture. So here we have V, and let's say here we have, again, W is smaller. So again, first of all, here we have Z, and then here we have W, doesn't matter really. And suppose you have the basis vectors, right? V1, and you'll see in a second, it's important to separate out the case up to K, and then Vk plus 1, Vn. That's in the input. And then in the output, well, we have the basis for Z, which is z1, up to zk. All right, and remember, our goal is to have it such that t takes all of v and maps it into this small space. And remember, there's this linear transformation extension theorem, for which I have a proof, by the way, on my channel, where I said in order to define a linear transformation, you just need to know what it does on the basis vectors. So you just need to know what t of v1 is, t of v2 is, t of vk, and then t of vk plus 1, and up to t of vn. Okay. And again, I like to think of it as follows. Suppose t is like a balloon. What this is saying is, if you know the strings of the air balloon, in some sense you can reconstruct the whole balloon. I can tell you exactly what it is. Seems weird in real life, but it is true in linear algebra. And let's see, how could you possibly define it? So you want t of v1, you want it to be in z, so that the range is z. Well, how about we just define t of v1 to be z1? It's a good first step, right? And then t of v2, how about we let it be z2? And then t of vk is zk. That's good because it tells you, well, the first k vectors, they get mapped in z. And what about the other vectors? Well, look, you want them to be mapped in z. And it's very important, none of those should be mapped to outside, because otherwise the range wouldn't be z. Well, here you have many choices. You could either let vk plus 1 be z1 or zk, or even easier, well, 0 is in that subspace, so take all the other vectors and map them to 0. So 0, 0, 0, etc., etc. Like this meme about this commercial, it's like 0 pores, 0 skin, 0 vector. Again, it's weird because I didn't say what t of x was. I just said that it's what it does at the basis vectors. But very important, this is enough by this linear transformation extension theorem. So t exists and is linear. And what does this require? It just requires the input basis. So what's cool about this is it doesn't really matter that we have this output basis in order to define v. T is a basis of v. Okay, and again, this is by the linear transformation extension theorem. But we do need the fact that the last thing is a basis, or at least a generating set, because what is the range of t? So there's a really cool thing about the range. In order to find a range, you just calculate t on any basis, and you find the span of those vectors. So it's really, in this case, the span of t of v1, if you want, t of vk, t of vk plus 1, t of vn. Okay. Which in this case, it's the span of z1, up to zk, and then a bunch of 0 vectors. But you see, 0 vectors don't affect the span, because if you take a linear combo of 0 vectors, you still have the 0 vector. So this is really the span of z1 up to zk. But remember, z1 up to zk is a basis. So the span of this is z. So precisely, the range of your linear transformation is z, and that's why this linear transformation works. And t is not unique, so depending on how you define your other vectors, you can let it send it to z1 or zk. That's also perfectly acceptable linear transformation. And why did we need z to be smaller than v? Otherwise this construction wouldn't really work. Because how can you have a small number of vectors and map it to a big number of vectors? That wouldn't work, and indeed, in that case, the result would be false. All right, I hope you liked this little exercise in linear transformations. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.